This is a good excuse to make another refraction video to help you understand that there's no other way it can work than bending light and you're living inside the concave Earth. Scott Leckie brought up the SSC, breaking the sound barrier. It passes from far right peripheral to far left in a concave shape. And so I checked that out, and this is good indication that refraction bends objects downward. Let's go back a little bit here. You see how the smoke trail, it's descending. See at the far distance, it's narrower vertically than it is over here. It's descending, and there's also another one over here. Check this out. Camera is stationed to the left of this, and it's far away right now. And you see it's beginning to rise. You see the horizon. It's a reflection. The horizon actually, it's creating this reflected image, but refraction is at play, and it's pushing objects downward from the distance. And you'll check out like the underside of the nose cone. You'll be able to see a little gap there. Now it's close. Now it's close to the camera, right? So you start seeing the gap. So the gap was rising, and now as it goes away, see, now you see a gap there, right? Okay, but as it goes further along into the distance, you won't see that gap under the nose cone, meaning that it's going down. Jeff Beck, going down. See, there's no gap there anymore. So that is proof positive that refraction is bending objects downward. And then you might ask, well, then how does the sun rise supposedly 2 minutes before due to refraction? And well, I point out this video here, I call it Refraction's Illegal Lift of Heliocentrism, and they will give you this graphic, this crude, silly graphic, saying that this purple line is allowing one to view objects farther into the distance because of refraction, and that's wrong. This is an illegal lift. They can't get away with raising this curve initially like that. If refraction were at play and you were on a convex ball, refraction would cause you to see less into the distance because refraction would bend it downward like that, downward. And so I made a video about this, explaining that when I was on the plane ride there. Talk about that.
To work with, your eye is down here inside the concavity of the Earth, and light is bending up. This darker purple line is the refraction line, and then there's a dotted line, which is a normal trajectory line. So the refracted horizon will be higher when it intersects the celestial sphere, like that. Same on the other side as well. So what it's doing, I divided up this very crudely. I divided up the area in which you observe under normal conditions. This line right here, this line right here, that's normal conditions. And so you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sections under normal conditions, but under refracted conditions you get 12 sections because you add these two here. And so because at ground level we only see 180 degrees, that's all we have to work with, you understand? From one side of the horizon to the other side of the horizon. So we have to compress, we have to fit, what did I say here? 12, we have to fit 12 sections into a normally viewed 10 sections, all within 180 degrees. So
Okay. And so I went into Wiki and found out that atmospheric refraction is actually causing objects to appear to rise, like the sun and the moon, celestial objects that is, mostly during or close to the horizon. Let's get that over here. And so I just made a little chart here. This is my my center point right there, and I divided up a circle into arc minutes, which is every 60 arc minutes is 1 degree. And so the sun is about 30 arc minutes, so it's about half of this. So that's the sun. So when you're looking at the sun at the horizon with refraction, the sun will appear about 35 arc minutes higher than it normally is in position over there. When you're looking at the sun, it's 2 degrees above the horizon. It will only rise up 18 as opposed to 35. And then when you're at 5 degrees, it will rise up 10 arc minutes instead of, obviously it's shrinking. You see how it's rising up mostly when the sun is at the horizon. So let's go up over to 45 degrees, and it's only 1 arc minute. It's barely anything at all. And then when you look straight at the zenith, it's 0. There's no refraction at all. So most of the refraction is taking place at the horizon. Okay, and now I'm going to take this graph that I made earlier and help to understand what's really happening within the concavity of the Earth. Your eye is down here in the bottom, right? And so under normal conditions, when there is no refraction, it's this light blue line like that, and it's rising up and it's inverting in orientation, and it's intersecting the celestial sphere. So this bottom half of the celestial sphere is what you see. It's an inversion in curvature. You understand? And so the purple line is the refracted line. And so you're going to see longer distance because refraction bends objects downward. And so even though you're inside a concave Earth and the light is bending upward, it's not going to bend up as quickly as the blue line. So it's refracted like that. You're seeing a further distance. This is the only way it works. It doesn't work on a convex sphere. Understand? And so that purple line is going to travel out like that, up like that, and it's going to allow one to see more than half, more than 180 degrees of the celestial sphere, and then bending light is going to be more affected toward the horizon. So it's compressing. I mentioned before how it compresses. And so this will help you understand too. These red lines here, let's get a normal shot first. Okay, here's the normal shot. We've got 180 degrees, right? We're seeing 180 degrees of the sky under normal non-refractive conditions. All right, and so this shot here is the refraction range. So you're going to see more than 180 degrees. These red lines are all equally spaced initially like that. So it reveals more than 180 degrees. Your sun and your moon are inverted in orientation or upside down. And so when refraction happens like that, you know, these red lines are more compressed now. They have to fit into the 180 degree range like that. And so now that's what we observe. This of the sky. That's how much of the sky we observe. It still has to fit 180 degrees, so it's going straight across like that, but it's compressing more at the horizon. And so it's going to compress the sun and the moon downward in this illustration, but because everything is inverted in orientation, it actually appears upward. So your horizon is still going to be apparently 180 degrees from the ground. But it's taking all this area here and pushing it down on this illustration to compress it toward the horizon. So that's why it compresses, it pushes. So it's pushing the sun and the moon downward. Refraction still works to push objects downward. It's just that the inversion is taking place and it fools the eye like that. Okay, I think this will really help you guys understand and help the smart people, you know, the physicists, the mathematicians, realize once and for all, convexism is busted. It doesn't work. There's no other way around it. You're in it. This is how refraction really works, guys. Okay? Ciao.